So guys, here we have the definition of an ellipse. It's the set of points such that the sum of the distances from a point to two fixed points is a given constant. So instead of all the distances from one point to the center, one point to all points around it being the same distance, it's when we add those distances together that we're going to get a constant value. So a couple notes about what all this means. And that's just what this little definition says here. Distance from a point to one focus plus a point to another focus is equal to a constant. And the focus is just two defined points. It's actually what we are defining this shape by, this ellipse by. So you get this figure right here. It's kind of like what happens if you were to take a center of a circle. So I took the center of a circle, and instead of having it as one point, I split it out into 2 points. Now the relationship between both of those back to all the points on the curve is going to be a constant sum of those two distances. For example, if I was to have these two, my F1, F2, my two foci right here, and I have a point out here on the curve, the distance from this point to F1 plus the point to F2 would be some K. We can say, I don't know, like 7 or something like that. So if I grab another point, say this one right here, the distance from point 2 to F1 plus point 2 to F2 would have to be the exact same value as last one. So in this example, 7. Or if I was to grab, I don't know, this point right here and go from point 3 to F2 and point 3 to F1 and add those two distances together, again, I would have to get 7. So that's what the definition of ellipse is saying. That from all points on the curve to both foci, you sum those distances together and you're going to get the same value no matter what point it is you've selected on the curve. So that's what the ellipse definition tells us. Now, a couple things about the ellipse. These foci are, the endpoints of this major axis are called vertices. It's the vertex on each end. On the minor axis, we have the co-vertices. The center is the center. Everything runs through the center. Major axis and minor axis are perpendicular. The foci, the vertex, the center, they all lay on the same line. So I'll never have foci on this short axis, on this minor axis right here. Now where I've got this ABC labeled, A is just the distance from the center out to the vertex. B is the distance from the center to a co-vertex. And C is the distance from the center to a focus. So we get this relationship between those three distances, that A squared minus B squared equals C squared. Not plus C squared, it's not the Pythagorean theorem. It's that A squared minus B squared equals C squared. So the square of my vertex distance minus the square of my co-vertex distance is going to give me the square of that focus distance. And yes, the plural of focus is foci, or foci, or whatever you want to call them. I'm going to call them foci. So that's the picture of what's going on with this definition. Now what standard form of an ellipse is actually going to look like, it has two different forms, and it all relates back to that major axis. Now keep in mind, A is the distance from the center to the vertex, and that's where we define our major axis. So if we have a horizontal major axis, we get x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. That's when we have a horizontal major axis. If I have a vertical major axis, we're going to get x minus h quantity squared over b squared equals, plus y minus k quantity squared over a squared equals 1. So as you can see, A is the distance from center to vertex. It's our longer distance. It's our bigger value. So whatever variable A sits underneath, the bigger number sits underneath, it's going to get stretched out further. Because these are just our transformations. Same transformations we've worked on. So we are stretching this component, this horizontal component, more than we're stretching the vertical component. So as I said before, it's like our circle standard form, our circle equation, but we're squishing it in one direction or another, or both directions, or stretching it out. So we're manipulating it, we're performing transformations on that. So if the bigger number is underneath x, then x has the bigger stretch. So it's a horizontal graph. If the bigger number is underneath y, then y has the bigger stretch. Remember, doing inverses when we directly apply them to the variable. So y has the bigger stretch, so we're going to get a vertical graph in that situation. But again, it still comes back to a squared, b squared, and c squared, or a squared minus b squared equals c squared, to put all that information together to make a graph for us. A is always the longer distance because it's always to the vertex. The vertices are the farthest points from the center. The co-vertices are the closest points to the center on our ellipse. So both of these formulas will come up, but don't stress so much on which one's A, which one's B, and bigger and smaller and all that stuff. Common sense is going to say you're going to do bigger number minus smaller number because I've got to get something I can take the square root of. And then just look at whatever's underneath x tells me how wide, whatever's underneath y is going to tell me how tall, and then the bigger numbers take care of themselves when it comes to graphing. So give me a couple seconds, I'll get some examples up here and we'll look at how to put all this information together to create our own graphs of ellipses. So here we have two examples that we're going to work through. And work through the first one, and I'll let you take a shot at this second one here. So as we're going through, we want to identify these key points, because all it is identify these points, put them on a graph, connect the dots, you've got your graph of your ellipse. So again, we've got our standard form right here. Center we're going to identify first, and that's the horizontal shift on x and y. So we can see that opposite of -3 is 3, opposite of -2 is 2. So our center is going to be sitting at 2. For vertices, we look at the larger denominator to get A. A squared is 25, so that means A is equal to 5. So if I was to put that on my graph right here, let's go ahead and start putting things on the graph. So 3, 2. So we've got 1, 2, 3, 1, 2. So there's my center. Vertices are going to be 5 units away from the center, and since it's underneath the x, we're going to go left and right 5. So left 5 puts us here, right 5 puts us out there. Pretend those are somewhat horizontal. Okay. Co-vertices come from b squared, which is our smaller denominator. So b is going to be equal to 3. So that means I'm going to go up and down 3 units from there, from the center. So up 3, down 3. And that's your ellipse. You get your curve from that. Just kind of connect it the best you can with a smooth curve. It'll probably look pretty bad like mine do most of the time. Some of y'all can draw really well, so you'll do a good job on it. But that's good enough. We can see the points. We want to write the coordinates now. I can go through and say, okay, that this is 3, 2, this is, sorry, 6, 2, no, that's, sorry, 3, 5, this is 3, -1, this would be -2, 2, and this would be 3, 8, 2. So we've written all our points. The way I prefer that you figure out what those are instead of counting around and everything, vertices are affecting the x on this one. So if I take my x coordinate and just plus or minus 5, that's showing left and right 5. Then I get my points. 3 plus 5 is 8, 2, and 3 minus 5 is -2, 2. So we get our vertices that way. Co-vertices are affecting the y's in this case, so I'm going back to my center. And I'm going up and down 3, so plus or minus 3. So we would get 3, 2 plus 3 is 5. 2 minus 3 is -1. So it's the same point. This just gives us a way to kind of look at it conceptually, where if we were needing these points when we don't have, and we don't actually need the graph, we just need the specific points, we can focus on what value that's changing. So 9 underneath the y says change my y's by 3. 25 underneath the x says change my x's by 5. That's really helpful when we get to the foci because you don't always get neat, clean numbers there that we can actually count. So foci, I've got to figure out what c is, but we remember c squared equals a squared minus b squared. So c squared we don't know, but we know a squared is 25, bigger denominator, minus b squared, which is 9. So c squared is 25 minus 9, which is 16. So c is equal to 4. Now, again, remember your foci lay on the major axis, the same axis that has the vertices on it. So, since the major axis is parallel to the x-axis, the 25, the bigger denominator is underneath x, then we're going to go with the foci running on our horizontal axis here, our major axis, which is right here, that ends in -2, 2, and 8, 2. So again, from the center, I'm going to go 4 units left and right. My y won't change, so I'll be left 1, up 2. So right here, and I will be 7, I'll go right 4, up 2. So 7, 2. So these are the 2 points that actually took this circle. This circle was sitting right here at one point, or these 2 foci were sitting right here at the center, and it gave us a circle. And as we moved them out towards the edges, it pulled this top down in. So we've squashed this in by stretching those foci apart. Real interesting thing happens, and maybe you should play around with this and see what actually happens if these get all the way out to the vertices. If you take your foci and get them all the way out to the vertices, what does the actual curve look like? So it might be something you want to play around with at some point. I think it's an interesting thing to look at, is how your graph looks at the extremes of those, what it looks like at the center, which we've talked about is the circle already, everything's equally spaced, and what it would look like when it's out towards the vertices. So we've got all of our points, we've got our center, we've got our vertices, co-vertices, and foci all on our graph. And if you want to, and I'm perfectly okay with it, if instead of writing all the points on the graph and it getting all cluttered, if you just want to list it out and just write, show your points, show your tick marks, all that stuff. But if you want to just write the center is this, vertices are those 2 points, co-vertices are those 2 points, foci are those 2 points, and just have a list of what your points are, and then put the actual points on the graph without the points labeled on the graph, and give a little bit cleaner picture. I'm perfectly okay with that. I probably actually prefer that to trying to cram everything in here like we have right now. But as long as you get it all in here, whether you want to draw it just like this, or whether you want to do the picture with no labels and then list out what the actual points are, either one of those is okay. All right, now we have this second example over here. What I want you to do is take a minute, pause the video, try to work this out, and give me a graph for that ellipse. And I'll wait right here. So hopefully you were able to come up with an answer, a graph. Let's see what you got. So starting with our center, opposite of this shift right here, so it says +4, so our x-coordinate is going to be -4. We don't see a horizontal shift on y, so that means it hasn't shifted from the origin, so the y is still going to be at 0. For vertices, we're going to do, let's pause on labeling stuff, and let's just put this information on a graph. Okay, some of you may react better to that. So let's look and see what we get. So center's at -4, 0. Underneath the x, we see 12. So horizontally, we need to be moving, and I don't care whether we're going to call them vertices or co-vertices at this second. Horizontally, we need to be moving square root of 12. So the square root of 12 is whatever, 2 square root of 3, correct? So left and right, 2 square root of 3. Well, 2 square root of 3 is 3 and a pinch. So 1, 2, 3, and a pinch. And then we'll go left 3 and a pinch. So there we are, 3 and a pinch. So that's what we do. Underneath x was a 12, we take the square root, we get 2 square root of 3, which is a little bit more than 3. So we go left and right 3. Well, underneath the y is 16, we do square root of 16, that's 4, so it tells me I'm going to go up and down 4. Again, I don't care whether these are vertices or co-vertices at the moment. I'm just thinking of getting my information organized on a graph. 1, 2, make these black. 1, 2, 3, 4, 1, 2, 3, 4. So that is my graph. So I get this curve right here, which is almost circular, which should give me an indication that my foci should be pretty close to the center. Now, which ones are vertices, which ones are co-vertices? Well, these are 4 away. These are less than 4 away. So that makes these the vertices because they're further away. So my vertices came from -4, 0, and I went up and down 4. So -4, 4, and -4, -4. Those are my vertices. My co-vertices came from when I took -4, 0, and I went left and right 2 square root of 3. So plus or minus 2 square root of 3, comma 0. And I would leave it like this because I can't evaluate that. It's an irrational expression. So just leave it -4 plus or minus 2 square root of 3. Foci, we know should be on, I pointed here a second ago, should be on the major axis, which is vertical this time because our vertices went vertically in this particular problem. So let's figure those out. So I'm going to take my a squared minus b squared equals c squared. So bigger denominator is a squared. Smaller denominator, the other denominator is b squared. That equals c squared. So c squared equals 4. So c is equal to 2. So my foci are going to be -4, comma 0 plus or minus 2 because my bigger distance went vertically. My vertices went vertically this time. So we're going to add the c, or add and subtract the c from the y coordinate. So for the foci we get -4 plus or minus 2, not -9, but -4 plus or minus 2. So it would be sitting right here and here. So you can see when they were a little bit closer to the center in this one, we had a more circular shape, but in the last one, when they were close to the vertices, we had a lot flatter shape, a more elongated shape. It had a greater eccentricity, as something we'll get to talk a little bit about later. The eccentricity of an ellipse tells us how stretched out our ellipse is. So again, you can give me the picture and then write your points in a table kind of like this. No problem at all with you presenting the answer like this. Here's my center, here's my vertices, here's my co-vertices, here's my foci, and then there's my graph. It gives me all the same information, and it's a little bit neater and more organized. So if you want to put it all in one, do that. If you want to write it out in table form, I don't care, as long as we get all the information on there. We know which ones are vertices, which ones are co-vertices. Vertices will be the ones that are further away. Co-vertices will be the ones that are closer to the center. So if you want to do like I did on this one and figure out which ones are vertices and co-vertices after the fact, once you've graphed them just by looking at which one's further away, that's fine. If you want to do it like I did in the first example where you look for larger denominator and you know that that's going to be the a, and then we put it with the coordinate that corresponds to the variable of which it is the denominator. All that probably just sounded like gibberish, but two different ways that you can go through and be able to organize this into a graph. So that's it for circles and ellipses. Key things to remember, center is HK, even though it says minus H minus K in the standard forms, we want to do the opposite of that. For a circle, it's going to be equal to the radius squared, so you square root that to figure out the radius, how far we are in all directions from that center. For an ellipse, very important, remember a squared minus b squared equals c squared minus. We'll do another one later on in another lecture with hyperbolas where it's a squared plus b squared, but this one is a squared minus b squared equals c squared for the ellipse. So make sure you understand that the ellipse gets the a squared minus b squared equals c squared to relate those denominators, those distances from vertices and co-vertices back to the foci. And that's pretty much it. Bigger denominator gives us our major axis, and the smaller denominator helps us get our minor axis. Okay guys, one last thing I forgot to put in there that we do need to do is be able to take a quadrant or take a conic from expanded form and put it back into standard form. So if we look at this example right here, we have this very large, ugly looking expression. We want to make it neat and combined and make it look like the standard forms do. We don't really know right now if it is a circle or an ellipse, so we really just have to get to work on it and see what we're presented with at the end. Because there's not much difference in a circle and ellipse in the standard form. Remember, they're both some binomial squared plus some binomial squared. The difference comes in the ellipse, we've divided by some numbers and it's equal to 1. And with the circle, there's no denominators. We're not dividing the terms by anything, and it's equal to whatever the radius squared is. So we just need to get into it and really focus on how do I get this into those binomials squared. Well, if you remember back from our work with quadratics, we do that by completing the square. Just like when we before took an expanded quadratic and put it into vertex form, we're going to do the same thing right here. But we're going to focus on just the x's and then just the y's. They don't impact each other. The x is going to have its own binomial that we're going to square, and then the y's will have its own binomial. So let's focus on the x's. Remember, first step is we've got to have a lead coefficient of 1. So I'm going to factor out the 2. Before we would have divided the whole equation by both sides. But because I don't want to mess with these y's at all, we're going to just factor out that. So 2 times x squared plus 2x. Leave yourself some room because you know we're going to have to add something in there. Plus, y's don't have a lead coefficient, so we'll just make them y squared minus 4y plus something. And we're going to put something in there equals negative 2. Because remember, first step really is move your constant to the other side. All right, so we've done that. We've got to insert b over 2 squared. Now, there's 2 different b's in this problem. So add b over 2 squared in here. So each set of parentheses has its own b. The x's have a 2 for the b, the y's have a negative 4. So we just go through and work with them. So it's plus 2 over 2 squared and plus negative 4 over 2 squared. Gives us 2x squared plus 2x plus 1 and y squared minus 4y, 2 squared is 4 equals negative 2. Now remember, when we keep our equations balanced, if I do it to one side, I've got to do it to the other. So I increase these parentheses by 2 over 2 squared, and since there's 2 of this quantity, I've increased that whole left side by 2 times 2 over 2 squared. Same thing here. I increase these parentheses with negative 4 by negative 4 over 2 squared, and since there's only 1 of this quantity, and I just go ahead and get in the habit of whatever's on the outside, I'm going to multiply by, so I don't forget it when it is there. So there's an understood 1 out there, so we'll just do 1 times that quantity. So you go through, do all your arithmetic. 2 times 1 is 2. 1 times 4 is 4. And when we clean it up, we get 2 times x plus 1 quantity squared plus y minus 2 quantity squared equals 2 cancels, 4. So at this moment, I don't have any denominator, so I'm asking myself, is this a circle? Do I leave it equal to a number? Well, the idea is, do I have a linear binomial plus a linear binomial squared plus a linear binomial squared? And the answer is no. I have a 2 times this linear binomial. So because I have that 2, I can't do that for it to be a circle. So this is most likely an ellipse, so let's divide both sides by the 4 to get it all equal to 1. And then you reduce 2 over 4 is a half. So we're going to get x plus 1 quantity squared over 2 plus y minus 2 quantity squared over 4, and that's equal to 1. So we have taken it from expanded form and put it down here into standard form. And we can get all the information from there to be able to graph. Center's at -1, 2. The major axis is going to be vertical. So we would go up and down 2 units to get our vertices. We would go left and right square root of 2 units to get our co-vertices. Foci is 4 minus 2 is 2. So we would go up and down square root of 2 because, again, our major axis is running vertically. That'll give us all of our information. We can get that quickly from our standard form right here. All right, let's look at this second example right here. If you want to, pause the video, go through and try to put this one in standard form on your own. If you don't want to do it on your own, I'm getting ready to go right through it. So let's look at it first. Remember, lead coefficients have to be 1. So I'm going to divide or factor a 3 out of this set of x's. So 3x squared minus 6x. Leave me some room. The y's also need to pull out a 3, so that's y squared plus 4y. Leave me some room, going to equal 0. Insert my b over 2 squared into both of those. So that's 3x squared minus 6x plus -6 over 2 squared plus 3y squared plus 4y plus 4 over 2 squared equals 0. Oh, but we've got to add it to the other side. So let's see what we've got. X minus 6x plus 9 plus 3 times y plus 4y. It's y squared plus 4y plus 4 equals 3 times 9 is 0 plus 27, and 3 times 4 is plus another 12. Clean it up. 3, or finish factoring it, minus 3 times x minus 3 quantity squared plus 3 times, what's that, y plus 2 quantity squared equals 39. And at this point, I don't have numbers in front of my, I have numbers in front of my binomials, but if I divide by 3 to cancel those numbers out, I'm left with a 1 in front of each one, which makes it look like a circle. X minus 3 quantity squared, y plus 2 quantity squared equals 13. So this one we will leave equal to a number instead of equal to 1 because we have a circle instead of an ellipse. And then as we talked before, remember, a circle is a special type of ellipse. We're going the same direction in both, the same distance in both directions. So realistically, you could write it as an ellipse by dividing by 13. And you would just be square root of 13 up and down, square root of 13 left and right, square root of 13 up and down, which is what we already knew because the radius is the square root of 13 and because the circle we go in every direction. So a circle is a special type of ellipse, and we can see that really well when we look at it in when we go through this, moving it from expanded form into standard form. All right, that's it for graphing circles and ellipses in standard form, and I will see you in class tomorrow, guys.